Welcome to Hot Chips 32. Session 1, Server Processors.
First of all, welcome to our first ever virtual conference. Back in January and February, we were planning for a physical conference, and then we had to make completely different plans starting in March. We weren't sure who was going to show up. We weren't sure what we were going to tell our sponsors about how it was going to be done. We didn't know how we were going to broadcast this. We didn't know where we were going to be broadcasting it from. But we did manage to pull it all together, and we're happy that you could all join us for this event. I'll let you know that I was quite worried about whether we would have anybody register for the conference, but I get to report that we have record registration numbers. As of this morning, the registration count was over 2,100 people and still growing. Our guys are on the line, helping all those last-minute people enter into the conference. At the time, when we started this virtual adventure, we didn't know what we were going to tell our sponsors about how it was going to work. But we do have a Rhodium sponsor. We'd like to thank Intel. Once again, they fully supported us, giving us funds to pay for some of the equipment that we needed to do this streaming live. And they're also paying for this lovely studio that we're standing in at the moment. So thank you, Intel. Thank you also to our Platinum sponsor, AMD, to all of our Gold and Silver sponsors as well. Many of these sponsors signed up for a virtual table this year. If we were at Stanford, we would normally have sponsor tables in the courtyard outside the auditorium, and you would all be able to visit those tables during the breaks or during any of the talks if you wanted to. This year, we set up a virtual courtyard on our webpage. So if you go to our conference webpage, hc32.hotchips.org, on the Sponsors Courtyard tab, you will be able to find links to the virtual tables for the sponsors who selected to have them this year. We also have Slack channels for many of these sponsors. You can engage them in chat. You can engage them in live discussions. You can read the information about their companies and their products on their sponsor tables. So please take a chance to visit them. Thank you to all of our sponsors. Now I'm going to, instead of telling you where to find lunch, I'm going to be giving you a virtual tour of our virtual conference. So we have a website, as I mentioned, www.hc32.hotchips.org. On the attendee page, this is a place where you can get help with logins and Slack access. So if you click that attendees link, down at the bottom of the page, you'll see our frequently answered questions, as well as the email that you should use if you need some help with any of your logins or getting to Slack, and a link to our Slack workspace. Also on that attendee page, I'm highlighting a few of the different features of our conference. We are having live videos, and if you're watching this right now, you are probably tuned in live. Look for that camera icon to find the live videos. Once we have finished recording a set of videos, we will be posting recorded video links, and you can find those with the smaller camera picture next to the EX posters on the right-hand side of this slide. The poster videos are already up for the recordings, and yesterday's tutorials are already up for the recorded videos. You can also find Slack links to any of the channels for our sponsors. Links. Okay. Sorry about that. As you can tell, we're in an entirely makeshift studio for this event. You can find links to our Slack channels for any of the talks, as well as for the sponsors and the posters. And on the day of the talks, yesterday's are already posted for tutorials, and today's are already posted for the conference. You will be able to find the PDFs. Tomorrow's talks will be posted at 7 a.m. tomorrow, so look for them then. On the tutorials and conference page, you will be able to find the recorded video link once it exists. You'll be able to see the schedule of the talks, and you will be able to find the Slack links and the PDFs for the various different talks. They are already posted, as I said, for the tutorials, the PDFs, and for today's conference. Last but not least, on our website, you can find the posters link to the 11 outstanding posters that our program committee selected this year. Please visit them. Many of these posters have recorded videos talking about their work. They have Slack channels if you would like to ask questions, and there's PDFs for viewing the actual posters. Now, behind the scenes, a conference like Hot Chips does not just happen. This is an entirely volunteer-run conference. It takes an enormous amount of effort from a large group of people in order to make it happen. We have a steering committee who's responsible for setting long-term direction for the conference, the organizing committee who is responsible for setting up this virtual video and all of our website and our Slack channels. They are helping you with registration. They're getting the word out through social media. They are making sure that all of this runs as smoothly as possible. We also have behind the scenes a large group of volunteers who are helping with the sound and the video on this delivery. And last but not least, we have a program committee who assembled an amazing program this year, which is why I'm sure you all decided to register. So I would like to right now introduce you to our program committee chairs. We have 2 program committee chairs this year. Priyanka Raina, who's an assistant professor in electrical engineering at Stanford, and Cliff Young, who is a researcher at Google and one of the designers of the Google TPU. At this point, I'm going to hand it over to Cliff to continue talking about this year's program. Once again, welcome you to everyone to Hot Chips 32. Take it away, Cliff.
Thank you, Elisa. Sorry, I can't quite hear myself. That seems better. Thank you, Elisa, for that wonderful introduction. And let me add an additional note of thanks to Elisa and to the organizing committee. Priyanka and I got to be flies on the wall at OC meetings this year and watch as Hot Chips pivoted from the 31-year tradition of in-person wonderful talks on a stage at Stanford to, oh no, let's make up something entirely new and do it for the first time in very little time to plan. The late nights that people stayed up working on this are really tremendous, and I'm very grateful that they were able to so seamlessly make the jump. With respect to our program committee, Priyanka and I had the honor of leading the program committee and picking our colleagues this year, and we have an outstanding set of program committee members spanning a wide range, academics and industrial people, people who have been with Hot Chips since its founding, people who just joined for the first time this year. I feel like the diversity and depth and strength of this committee reflects the incredible things that are going on in the hardware and chips industry today, that it's a wonderful moment to be doing computer architecture and to be building new chips, that we also have an incredibly strong program of chips in established areas like servers and mobile processors and GPUs, although we have new versions of each of those this year, and we have incredible innovation in a number of areas, particularly networking and my own favorite, deep learning. So thank you very much to the program committee. Let me add, we only got to have one in-person program committee. Normally the Hot Chips program committee meets about 4 times over the course of its operation, but of course COVID prevented us from doing that. I cannot think of a group of finer people who worked tirelessly, first recruiting talks and then picking the program this year. And lastly, each of the session chairs worked tirelessly with the different speakers to refine their talks and make sure they're prepared for the virtual environment this year. There's a huge amount of work that went in behind the scenes, and thank you to each of the people in my committee for their help this year. If you tuned in yesterday, you saw 2 really strong tutorial presentations. The first organized by Paulius Misikavicius of NVIDIA about machine learning training scale-out, which is certainly near to my career and interests and to a large fraction of our industry today. It's a place where architecture and high-performance computing and the forefront of scientific exploration meet, and to have some of the leading lights of that field, both on the systems building and on the systems using side in one tutorial was incredibly valuable. If you didn't have a chance to watch it live, I'd highly recommend tuning in and checking it out. And similarly, for the second tutorial yesterday, Misha Smilyansky of Facebook from our program committee organized a tutorial about the state of quantum computing, and that had leading lights once again from all of the major groups that are building quantum computers, that are racing to bring that technology through the different cycles of advance and settling and figuring out exactly how to get to that. It was a glimpse of our potential future here at Hot Chips, even though they pointed out very, very keenly that many quantum computing chips operate near absolute zero, so perhaps they're not especially hot. That was also a wonderful tutorial, and I would recommend taking a look at that. And for the last part of my section in the introduction, I get to talk about our two keynotes. We have one today by Raja Koduri of Intel. I will refrain from reading all of his titles because there's a litany of them, but he is talking about No Transistor Left Behind, and I would expect him to give us a view of how Intel sees the whole industry across their entire set of product lines, mobile, embedded, through servers, and their new entries into GPUs. I will add that, actually maybe changing pace just a little bit, in our field, we very recently lost Fran Allen, who was an incredible pioneer in both compilers and computer architecture. She was the first woman to be an IBM Fellow, the first woman to win the Turing Award. And I think that looking over the contributions of her work, in many ways, she invented the hardware-software interface and was the person who pioneered the concepts that I now call co-design and that underlie so much of the work that has been just central to my career. As part of his keynote, Raja will air a tribute to Fran and her career. I would strongly encourage you to tune in this afternoon to see that keynote. Tomorrow, my colleague Dan Beloff, who's a distinguished engineer at DeepMind, will talk about the perspective from DeepMind and their unique approach to the artificial general intelligence problem, the scientific neurobiological basis for that, the philosophical aspects of the way that they train and deploy networks, and also I think he's going to throw the gauntlet down and tell us the ways in which we really need to change our systems and computer architecture game. I think Dan's keynote tomorrow afternoon will be a wonderful way to anchor the second day of our conference. And I believe that's it from my section of the introduction. I'll hand it off to my program co-chair, Priyanka Raina.
This program, we sent out a call for submissions and received 88 abstracts from across the industry and academia. Each of these 88 abstracts was reviewed by each member of the program committee, and from those, we accepted 25 talks to be presented at Hot Chips. We have organized the talks into 8 sessions, 4 today and 4 tomorrow. Today, we will start off with a session on server processors, where Intel, IBM, and Marvell will talk about their latest CPU architectures. Then we will move on to mobile processors, where both AMD and Intel will talk about their next generation mobile CPUs, Ryzen and Tiger Lake, respectively. After Raja's keynote in the afternoon, Alibaba, ARM, and Harvard will talk about their edge computing platforms. And then finally, we will conclude the day with the latest GPU and gaming architectures with talks from NVIDIA, Intel, and Microsoft. While today's program will focus more on general purpose computing architectures, tomorrow's program will focus on domain-specific architectures. This will include FPGAs and coarser-grained reconfigurable architectures, specialized networking chips, and finally, chips for machine learning training and machine learning inference. The Q&A for all sessions will happen through the Hot Chips Slack workspace. You should have received the link to join Slack in an email. Once you join Slack, you will see a window like this. On the left-hand side, you will see several channels. Each talk has a dedicated Slack channel. Please use these channels to post questions about the talk during the presentation. The session chair for each session will pick questions from Slack and ask them live to the presenters at the end of their talks. When entering questions to Slack, please type in your name and affiliation. If we run out of time before we answer all your questions, speakers may answer questions directly in Slack later. That being said, enjoy Hot Chips. I would now like to welcome the session chair for our first session, Pradeep Dubey.
Be talking about. and one of the lead technologists at Intel, driving performance architecture and analysis for a number of Xeon servers. From 1996 till 2004, she worked on numerous IPF product architecture definitions. In 2005, she took over Marome, based on Xeon DP and MP product performance projection responsibilities. In 2007, Irma became the technical lead for Nehalem EX pre and post silicon, for which she received an IA award. Post Nehalem, she has been focused and delivered on multiple successful products, server products, Ivy Bridge, Skylake, and now here to talk to you about Icelake. She's mother of 2 adult children and married to her husband for 24 years, enjoys traveling, painting, choral singing. Here's Irma. Irma?
Talking about the new 3rd generation Intel Xeon Scalable processor called Icelake this morning. Here is an introduction to Icelake. Icelake is the CPU that uses the 10 nanometer plus process technology. It is the CPU that goes into the new Whitley 2-socket platform, which is shown on the right. It is the CPU that incorporates Sanikov core, bringing it to Xeon server. And it is the CPU that brings scalable and balanced architecture to the data center for increased throughput as well as increased per-core performance across all server usages. With that, let me show you what we are going to go through today. First, I'm going to show you and talk a little bit about the Sanikov core, the microarchitecture and the new ISA and the usages in server. And then I'll shift gears and spend majority of my time talking about the rest of the SoC infrastructure, the architecture, and the optimizations. Let's look at the Sanikov core microarchitecture. The diagram shows you in details that you probably know from the Icelake client introduction, but quick repeat, we have an improved front end. We have higher capacity structures as well as a better branch predictor. We have wider and deeper machine. Our allocation is now 5 wide instead of 4 wide before, and execution is also wider up to 10, and we have larger structures all around. And we have also other enhancements. TLBs are larger. We have much better single thread operation performance, and we have better prefetching. And last but not least, we have the server enhancements. So the core, just like the prior cores, comes with larger mid-level cache for server. Our mid-level cache grows from 1 megabyte to 1.25 megabytes on Icelake, and we do have the second FMA as well. And the table on the right is showing you the structure sizes, and you can see how much increases there are in all of them. With all this, at the end, today in our pre-production samples, we are measuring around 18% IPC increase for geo-mean spec-int rate workloads. And this is with ISO core count, ISO frequency, and ISO per core bandwidth. You can imagine that if we were to do ISO core count with higher per core bandwidth, we could get much higher IPC as well. Let's look at the new instructions that I mentioned that Sanikov brings. They are targeted particularly in 2 areas, optimizing 2 areas, cryptography and compression and decompression. On the cryptography side, we have the big number arithmetic instructions, like the VPMet52, useful for public key cryptography. And then we have the AES instructions that are vectorized in this generation, vector AES and vector careless multiply instructions. We have the Galois field new instructions, which are again targeting encryption algorithms and error correction algorithms. And then we have the SHA new instructions for secure hash algorithms. On the right-hand side, you see the bit algebra new instructions and the vector bit manipulation instructions. And these are particularly useful for database, dictionary accesses, data mining operations, etc. Now, let's take a look at what we are observing today, what we are able to achieve at Intel on our engineering samples. On our engineering samples, we are using the new instructions, the SIMD ABX512 on Icelake. The left-hand side is showing you the instructions used for these particular algorithms that I'm showing, ciphers that I'm showing on the right. And we are using those instructions with new software techniques and algorithms. Our crypto team has spent tremendous amount of time, and they have used some of the techniques are listed on this slide, like the multi-buffer and function stitching techniques. These are not necessarily new. They have been used before, but now they are being used in concert with these new instructions. And on the right-hand side, you can see these are most widely used cryptography ciphers today in the industry, and we are seeing unprecedented performance increases at a per core level when we compare Icelake versus Cascade Lake at ISO core frequency. So I hope you get excited about this, because we certainly are as we see these results, and the improvements keep coming. So you are seeing here our existing ABX512 hardware that has been introduced in prior generations, now being used with the new ISA and with better software techniques, improved software techniques and algorithms coming together and resulting in excellent performance increases. So we are certainly excited on this. I'm going to leave it at that and switch gears to SoC now. We are going to talk about infrastructure architecture first, and then we'll go look at how we put the SoC together, and then we'll talk about a little bit about the memory hierarchy and the IOs, and then some of the optimizations. So first, let's look at our infrastructure and the control structure. What did we do? What were we doing before, and what is different? So we created a new microarchitecture specifically for infrastructure. Our goal was to create a consistent communication channel across all IPs and our control units. And this is for both control as well as telemetry. So in this generation, we basically introduced two new fabrics, one dedicated for power management and one for general purpose. You see the green box is our power control unit, which is sometimes referred to as P unit. It houses our firmware as well, and that unit has to communicate effectively with all the IPs and subsystems on the SoC. Same way, the yellow or orangish color manageability and RAS services unit again has to communicate with all the IPs and subsystems in order to set up the right configuration, to set up the right registers, and to do the error handling. So it's really key backbone of our architecture. And with this, what we did was we basically streamlined the communication. Each of the IPs and subsystems, as you see, has a power management agent, which effectively abstracts the IP-specific behavior and implements hardware FSMs for all power management control and telemetry. This way, the control unit doesn't need to know the details of each IP, and the PMA can do the control and management for voltages, frequency ratios, etc. Same way we do the control for our manageability and configuration as well. Streamlined, dedicated telemetry, and with this we are able to improve our responsiveness greatly for all the power management and control changes. And also the next thing it does is it helps us with scalability. As we add new IPs or more of the existing IPs, our infrastructure scales seamlessly, and building new SoCs becomes much easier. Now that you saw the backbone, let's go see how the architecture, the rest of the architecture is put together. On this slide, what you are seeing is, on the left-hand side, the prior generation server Cascade Lake. It's 28 cores. And on the right-hand side, you have a picture of Icelake, again, a 28-core example. And as you look at this first glance, what are the similarities and differences? In a way, there are quite a few similarities. You do see the horizontal and vertical rings That's our on-die coherent mesh fabric. It's very similar to the prior gen. And then you are seeing the tiles. We do have the core and last level cache tiles, which house our caching and home agent and the Snoop filter and the last level cache. So those tiles exist again here on Ice Lake. What that means is, yes, we have still the distributed cache, and the entire cache on the die will be accessible by all cores at uniform latencies. We try to maintain the balance and the large cache size capability. And the other thing that you see is we have on the north we have IOs, and on the south we have IOs, instead of just having IOs on the north of the die. So that is yet one more thing we did because we wanted to have more edge space. And you also see that on the south we not only have IOs, but we have also some core cache tiles. So we wanted to utilize our die area as much as possible, and that's how we got there. So let me start talking about IOs and memory hierarchy a little more on this slide. So on there, maybe hard to read, but you can see we have those light blue boxes that are called out for PCIe Gen 4. Indeed, we are integrating PCIe Gen 4 controllers on Ice Lake, and they are fully compliant, and they support NTB, all the normal PCI operations that you can imagine. What is new is that we have a new virtualization implementation on Ice Lake, and with that, it's a faster design. It has larger TLBs, and it supports large page sizes for in-translation requests if the device supports it. And with that, we are able to get up to 3x bandwidth increase with virtualization on this generation compared to the prior generation. So effectively, we are able to hit native performance with virtualization for large packet sizes. And the other new thing about I/O is we put a fabric which is not visible externally, but it's credit fabric implementation that is on the north and on the south rows, those caps that you are seeing where there is I/Os. And the whole purpose of this fabric is to enable fast peer-to-peer communication and enable high bandwidth capability for those. So our goal is to hit our Gen 4 targets. The next thing I want to highlight is the UPIs. Those orangish boxes you see on the right are 3 UPIs. And what we did was it's basically we split the UPIs. This way, each UPI agent has its own fabric stop, and it has its own PLL, and it could be independently clocked as well. Then let's look at the light gray boxes on the right. Those are our memory controllers. Maybe hard to read, but they each have 2 channels of DDR4 memory, and they are ground-up designs, and they are designed with efficiency in mind. So with the new memory controllers on Ice Lake, we can get the best efficiencies across all frequency ranges. And we also support the top DDR4 speeds. The other thing that is new is the total memory encryption that comes on Ice Lake. It is implemented in the memory controller, and it does the DRAM encryption using the AES XTS 128-bit keys. And the key is hardware generated. You enable this feature in BIOS. You do not need to do anything special from the software. And when it's enabled, the entire memory is encrypted. And the key is not accessible by software or BIOS. And I guess one other piece is that the key is per part unique, hardware generated key. And in terms of overhead, if you wonder, today we are measuring a few percent performance impact and not more. On the memory hierarchy, we also support, like prior generation, Optane persistent memory, this time the 200 series. And this comes with at the top DDR4 speed as well, and it has a better power profile. Again, our goal is scalability, and that's what we were trying to accomplish by putting all these features. Next, let me go a little in depth into some of our performance optimizations. We have a number of them here, so I'll try to go fast. The first one is dynamic prefetch throttling, DPT. It's a new core SoC handshake mechanism that we introduced on Ice Lake. With this, we are able to modulate prefetches under heavy memory activity in the SoC. And with that, actually, we are able to get significant goodness from our LLC prefetches. In the past, you might know that LLC prefetches at the time sometimes were hurtful to performance and sometimes very useful. So we used to recommend to our customers for some workloads to turn them on and for some workloads to turn them off. With this feature, we do not need to do that anymore. Dynamically, we can get the best of the worlds. So, and over there, what you are seeing is a micro benchmark benefit. So you can, of course, run a test and see the benefit, but we expect that in real-world workloads, we will get the benefit of this as well. Spec I2M optimization is the next one. It's a optimization implemented in the core. The core, when it gets the read for ownership and write back requests, it checks if it's a full line write back or not. It has that information. And for full cache line write backs, if the core can get informed about the memory bandwidth usage in the on-core, could then decide to do RFOs or spec I2Ms. And that's what's happening with this optimization. Because of DPT, the core knows if the SoC is under heavy memory utilization or not. And when it is, it turns those RFOs to spec I2Ms, which then end up saving a memory transaction. And it helps increase our streaming workload performance quite a bit, as you see over there, up to 25%. Non-temporal write optimization is the next one, and this one targets low core count active throughput and single core or low core count non-temporal write bandwidth increases significantly with this optimization. What we do is we do not wait for collecting Snoop responses, and we pull the data from the core early, and this tremendously helps for those low core count cases where the latency was hurting them, really. That Snoop response collection latency was hurting them. The next one is IODC, Directory Cache Extended. We have the directory cache in the prior generations, and it was used for remote writes from I/O. PCIe writes were utilizing this and were able to reduce the memory overhead, memory directory overhead for remote socket writes. And now that is extended for core writes as well. And again, you can get good upside by using this. For non-NUMA workloads, of course, not for NUMA optimized workloads. The next one is the OSP extended, and this is basically the opportunistic Snoop broadcast that we had. Now it's extended for new opcodes, so reads and RFOs could also benefit from this. And by doing so, we can reduce the remote socket cache-to-cache transfers quite a bit. The latency reduces by about 70 nanoseconds. The next one is hemisphere mode, and this one is our default mode operation for socket UMA interleaving, and it optimizes the memory latency basically by minimizing the distance between our caching agents and the closest memory controller. And with that, the saving is roughly 2 nanoseconds. It may be not much, but still, every little bit latency saving helps. The next one is, and it needs a symmetrically populated memory configuration. The next one is M2I optimization. And what we do here is, within the socket, let's say a core has some data, it had modified it, another core comes and requests that data. In the past, we sent that modified data to the requester, but kept a shared copy of that line in our private cache. With this optimization, we sent the modified data and we invalidate our own cache. We no longer have it. So if the requester was going to do, let's say, a compare exchange and write to that line that it read, it doesn't need to come back and invalidate a line that was left in shared state in the new implementation. So we expect this is going to improve our OLTP, DB, database type workloads for performance, and that was our motivation, really. We had analyzed those workloads, usages, had characterized it, and that's how this optimization came to be. So that was a flavor of our performance optimizations, and here you are seeing two graphs showing you memory, bandwidth, and latency on Ice Lake versus Cascade Lake server. X-axis is bandwidth, Y is the latency, and you can see in left and right, both cases, bandwidth increases are greater than 45%. When you look at our memory speed and memory channel count increase, at most we should be getting 45% bandwidth increase on this SoC. But with the improvements that some of them I mentioned earlier, for instance, the left graph is a 3-read 1-write with RFOs. So that particular graph is showing the goodness of that spec I2M optimization that I mentioned in the last page. And the right-hand side is with non-temporal writes, but all cores active, so it's not the optimization I mentioned in the last slide, but earlier when I mentioned our memory controller has improved efficiency and our overall SoC has better scaling, that's how we are getting the better scaling for the right one. Let's move on and look at some of our power management features. A few that are important for performance. Power management latencies. Our goal was to minimize the impact from these power management latencies. For instance, our P-state transitions, our frequency transitions, they were costing quite a big bit of latency and hurting some performance, especially our network communication workloads were getting hurt. And for that, what we did was we did two things. One is the fast core frequency change. This one is achieved by a new PLL. We have a new PLL design that allows us to change frequencies in a continuous sweep without stopping the clocks and relocking and needing to wait for a while before locking. We don't need to do that anymore. So it's fairly instantaneous and allows the P-state transitions to be not visible almost to our benchmarks and to our workloads. On the right-hand side, you are seeing actually a graph that is showing it's a micro benchmark and that is doing a fixed amount of work every iteration, and every 10 or so iterations, you are seeing this step function type of thing where frequency is changing, core frequency is going to 0.2 to 0.1, and you see that on the red dots, which are for CLX, and they actually are spiking up every time that frequency change is happening. And on Ice Lake, we don't have that anymore. You don't see any blue dots up there on the top, and the spikes disappear. So that is basically that fast core frequency change feature in action. And the next one is the coherent fabric drainless frequency change. So as we did that frequency change, clock, stopping the PLLs and then relocking them, as I mentioned, we also used to drain the buffers and then restart the clocks. Now we don't need to do that anymore. That again helps tremendously and reduces frequency transition costs by almost 3x. And you are seeing on the right bottom table these reduced latencies for transitions that we are seeing now. Next, I'm going to touch upon our AVX frequency improvements. As you know, we have brought AVX 512 in Skylake generation, and it came out, our frequencies were fairly low compared to SSC frequencies when we started using those instructions, and because of that, software hasn't really made too much use of those instructions. So our goal has been since then to minimize the frequency impact. And what we did was we looked at the usage, how much power each of these instructions are really using, and we said, let us not penalize all the instructions equally. If they don't consume much power, why should they lose frequency? So with that, we categorize them, and we then are able, in this generation on Ice Lake, do that smarter mapping between instructions and their power levels, and we don't need to lower the frequency as much. And what you are seeing on the right bottom graph is that those blue dots are Ice Lake, the reds are CLX, and the dark blues are Skylake. This is a chart where we are showing relative frequency compared to the SSE frequency. These are all turbo frequencies, but our relative frequency compared to SSC for this AVX 512 heavy, and light. As you see in prior generation, it's dropping quite a bit. And on Ice Lake, the blue dot, for instance, for AVX 512 light and 256 heavy is pretty much at the SSC level. Our target is to operate at the same speed as SSC. And for heavy 512 operations, we are losing frequency, but look at how much the drop is on CLX versus on Ice Lake. So it's improving very, very significantly, and this is very encouraging. We expect that our software writers are going to make much greater use of these instructions on Ice Lake. And in fact, on my way here, I was speaking with one of our engineers who was telling me that he's seeing performance upside on the same code on Ice Lake compared to CLX, when on CLX we were actually dropping performance, and on Ice Lake he is seeing up to 10% goodness. So this is very exciting for us. Next, let me talk a little bit about our speed select technology set of features. This is an umbrella of features or a suite of capabilities basically to allow us to reconfigure the processor dynamically. And basically, based on the needs, what's running on the server, what's being consolidated on the server at a given time, our customers could choose and maximize performance using these capabilities. There are 4 of them. I'll start on the left top. That's the performance profile feature of SSD. And what that does is basically allows us to get a part, but then that part could be modified to another performance profile. Up to 3 performance profiles are possible per part. And for instance, the customer could choose to take a 24-core part and then turn it into a 16-core and different TDP part, or make it another 8-core part, depending on the use case, depending on the speeds and the power levels that they want to operate. They could actually take one physical part and turn it into 3 different parts, and they could do this dynamically at runtime. They can discover it and they can deploy it. The next one is core power feature, and this one, what it does is it basically says the high priority cores should take more of the more power versus the lower priority cores. So instead of dividing up the power across all cores equally and fairly, we can prioritize some cores to take more of the power share and hence generate more performance. So if you have a critical task you may want to run on, you can prioritize those cores higher and they could get to higher frequency points. Then the next 2 are a little similar in nature. One is to prioritize the base frequency, and the other one is to prioritize the turbo frequency. So depending on the usages, some may not want to enable turbo, some may want to enable turbo. If they have critical tasks that they need responsiveness, the very quick feedback, and they are critical to finish, they could prioritize the number of cores for higher frequency and run those workloads on those cores, while the background work could happen on the lower priority cores. Of course, as we increase the frequency of some cores, the rest of the cores' frequency will drop, but as long as you are able to prioritize your work properly, that should only benefit and help maximize performance. With this, some of these features actually were introduced. For instance, power profile was introduced in prior generation, but it was not dynamic and it was not discoverable. So, and the rest are new, and altogether, this feature set we think is going to be really critical to use in our cloud use cases by our cloud customers. In summary, Ice Lake is the first Intel Xeon scalable processor using the 10 nanometer technology. It does bring our Sonikov core to market for the Xeon market, and it is able to improve per core performance very significantly on existing binaries. And as we talked on the new instructions, it's also introducing new instructions, and the new software innovations with existing and new instructions will lead to unprecedented performance increases on this processor. And with new scalable infrastructure, the power performance optimizations, Ice Lake achieves both high throughput and per core performance. We do know that the critical need for highly balanced systems continues. Systems that can deliver high scalability in performance, as well as software responsiveness for all workloads that are consolidated simultaneously on the system. And Ice Lake will be the CPU that will bring a balanced CPU for all server usages. That ends my talk, and I would like to give some special thanks to these individuals who have contributed to this presentation, as well as the entire crypto team and our Ice Lake architecture, design, validation teams, and the program management. Thank you very much for your attention.
Thank you, Irma. Thank you, Irma. As you saw, the talk took a little longer than we expected, so I'll just have less time for questions. But let me ask the most important question, or the most frequently asked question here on Slack channel. What is the performance impact of enabling, how much performance is lost when TME is enabled?
When TMB is enabled, our target was, when we were designing it, not to lose more than 5%. But today on pre-production samples, we are seeing 1 to 2% on the experiments we have done, at most loss, and not more. So relatively small overhead. Sorry, I'm unable to, something happened with my camera. It was working while I was waiting and no longer. So
that's okay, we can still hear you.
Yes, I can hear you.
Okay. Yeah. The second question, regarding the AVX frequency improvement, you gave the power unconstrained turbo frequency example. How will base frequency scale for AVX 512?
The base frequencies, yes, I gave the turbo example and relative frequency change compared to prior generation. And for base frequencies, similar improvements will apply. So we will have similar reductions of less loss of frequency for similar instructions, basically. I can't hear you anymore, Pradeep.
Yeah, okay. And so the last question, will Intel support additional crypto algorithms? Okay, we're moving on now to the next talk.
I couldn't hear you.
Okay, the question was, will Intel support additional crypto algorithms?
Yes, it will. And the ones, in addition to the ones I showed, I think I showed you 10 algorithms. We are working on a number of them. And in case, some of you are interested in certain algorithms, please reach out and let us know. We'll be happy to provide them to our crypto team for further optimizations.
Okay, the next question is, what is the change in the PCIe that helped improve bandwidth for virtualization?
We have a new virtualization engine design. Basically, the TLBs are larger. We have that BTD IOMMU is now running at double the speed compared to prior generation as well. Also, the large page support is now for translation requests as well. If the device is supporting it, we can do it. So those are all new. That's how we are getting more than 2x improvement.
Okay, last question, then we have to move on. You mentioned 18% performance IPC increase at ISO core frequency. How does it compare with Cascade Lake, Cooper Lake?
The IPC improvement is basically against the Cascade Lake or Cooper Lake, right? They were the same architecture really previously. So it comes mainly from the core improvements that was shown, microarchitecture enhancements. And if the question is more at the SoC level performance, I won't be able to comment on that today, but we will be seeing substantial performance increases at SoC level over Cascade Lake and Cooper Lake.
Okay, thank you, Irma. To all the listeners and attendees, please keep asking your questions in Slack, and we during the day, Intel team will be answering those. Our plans to answer many of those. Thank you. So let's move on to our next speaker. And next speaker is actually a pair of speakers from IBM. The next talk is on IBM Power10. And the first speaker, and William Starke is an IBM Distinguished Engineer currently serving as the Chief Architect for Power10. Since graduating from Michigan Tech, Bill has been employed by IBM for 30 years in several roles spanning mainframe and power system performance analysis, logic, and microarchitecture. In fact, two of us probably overlap there. No stranger to hot chips, Bill presented the Power7 processor 11 years ago and has collaborated on Power8 and Power9 presentations since then. Brian Thompto, the second speaker, is an IBM Distinguished Engineer currently serving as the Chief Core Architect for Power10 processor. Since graduating from University of Wisconsin-Madison, Brian has over 20 years of experience leading global development team across 10 generations of IBM Power and IBM System Z server processors. Brian presented a Power9 processor at Hot Chips in 2016. So without further ado, let's start with the second talk of the session.
Greetings. I hope this message finds you safe and in good health as we all find a strange new way to do hot chips. As Chief Architect of Power10, I'm going to talk publicly for the first time about Power10's system capabilities. Then I'll hand it off to our Chief Core Architect, Brian Thompto, and he will unveil the core's capabilities. But first, a little context. Over the 10 years shown here, and many more before that, Power has been fundamentally about the enterprise and about extreme scale. This isn't some consumer-grade piece of high-tech jewelry. It's not under the hood of a beautiful new automobile. It's the building block for the world's most powerful supercomputers, applied to science, to defeating COVID-19. Even more importantly, it powers the systems that enable our world to operate: financial systems, commerce, healthcare, governments. Power10 is built for the enterprise of the future, one that is mobilized by cloud capabilities and made smarter by AI technologies, a bulletproof fortress of security and resiliency. We have first hardware back in our labs, and we are making excellent progress toward testing the chip and the first wave of systems. We are on track to delivering Power10 systems a little over a year from now. Today, we'll talk about Power10's data plane, built upon bandwidth, enabling multifaceted connectivity and scale, about the enterprise strengths of the core, about new security capabilities co-optimized across the stack, about from the ground up re-architecting for energy efficiency, and finally, about the maturing AI landscape. Just as we hope for our children, AI models grow up. They graduate from training and get jobs in the real world. Acceleration needs to get pushed into the processor core, infusing AI directly into the enterprise workflows. So here is the chip, a beautiful photo thanks to our partners at Samsung Foundry. 18 billion transistors in Samsung's 7nm technology, and with a few IBM tricks baked in, courtesy of our rich research and development collaboration. 2 packaging options, but I'll get into that in a moment. We also have 2 variants of our core, a smaller 4-threaded version and more powerful 8-threaded enterprise version. Today we'll talk about the enterprise core. We offer up to 15 per chip, each with 2 megabytes of L2 cache, backed by a robust 120 megabytes of L3 at the chip level. Those with a keen eye will notice 16 physical cores on the chip. We tend to get high demand for our highest core count offerings. Having a built-in spare vastly improves the economics of servicing those demands. We feed these powerful, hungry cores with a massive data plane interface to the outside world. The chip perimeter is filled with high bandwidth, low energy PHYs, comprising our OMI and Power AXON signaling infrastructure, as well as our PCI Gen 5 I/O attach, but more on these later. Power10 comes in 2 packaging form factors. The single chip module maximizes energy and data bandwidth per core. It also provides topological flexibility for systems ranging all the way up to 16 gluelessly connected Power10 chips. The dual chip module maximizes dense compute throughput and I/O connectivity by compromising energy per core and memory attached per core while limiting SMP topologies to 1 to 4 sockets. When people talk about cloud, they often think just about 2 and 4 socket systems. With our Power10 dual chip module, we gain impressive strength there. But cloud isn't only about force fitting into those form factors. By optimizing our 16 socket big iron systems for cloud as well, we enable scale and elasticity far beyond what any small system can provide. Last year, we introduced the Power-AXON and open memory interfaces, which are foundational to Power10. Built upon high bandwidth, low latency, low energy SerDes technology, they run high lane counts at up to 32 gigatransfers per second using straightforward packaging, 150 micron bumps. The result is a combined 2 terabytes per second per Power10 chip with optimized placement for module and system planar simplicity, more economical than expensive microbump packaging for achieving bandwidth, and more flexible, enabling pluggability and even cabling for distance. These are both highly flexible interfaces, but first, let's look at how they are used for more conventional purposes, yet provide unconventional value add. In Power10, Power-AXON is used for all chip-to-chip SMP connectivity, from small 2-socket systems to the largest 16-socket robustly scalable systems. No ASICs or NUMA controllers, just 16 Power10 chips, a whole lot of bandwidth, and several decades of coherence, transport, and protocol innovation. So what will Power10 add for the large enterprise space? We've built in compute capacity growth, a stronger thread, more bandwidth, and several new scaling capabilities. Compared to an already strong Power E980 system, Power10 Big Iron raises the ceiling substantially higher. OMI memory, which we introduced here last year, is the grandchild of the Centaur memory we unveiled here several years ago along with Power8. It is technology agnostic, so it can attach to any memory media with an OMI compliant buffer. Since DDR4 DRAM is still the bread and butter of the main memory tier, Power10 will launch with the OMI DDR4 buffer chip built by Microchip that we introduced here last year. The cost and bandwidth efficiencies enable up to 410 gigabytes per second of peak DDR4 bandwidth per Power10 chip. That's at a chip level, not a system level, while incurring less than 10 nanoseconds of extra latency. They've built an impressive solution. And the nice thing about OMI, when DDR5 is ready, we can simply replace DDR4 DIMMs with DDR5 DIMMs. No new system, no new processor chip. Looking at broader possibilities, consider a GPU, rigidly packaged with HBM memory on an expensive microbump module. Using a GDDR buffer in a standard OMI DIMM form factor, you can push 800 gigabytes per second sustained without the rigidity or cost. Not quite the bandwidth HBM can push into a GPU, but highly differentiated for a general purpose processor. Or, at the other end of the spectrum, you could put a high capacity persistent storage class memory into a standard OMI DIMM form factor. Might be a nice way to start filling up Power10's 2 petabyte physical address range. Power10 also supports OpenCAPI, an open asymmetric protocol for coherently attaching compute accelerators, memory devices, networking, and storage, which first showed up in Power9. The memory piece of the protocol, like OMI, is well suited to attaching storage class memory, but in a device slot or cabled external enclosure instead of a DIMM slot. Power10 introduces a bold new member to the Power-AXON family, Memory Inception. As the world evolves toward cloud, the economic promise of disaggregated infrastructure has been a tantalizing proposition. Marketing chartware describing rack-scale architectures and iconic names like The Machine inspire the dream of extending resource sharing beyond the server. Power10 takes a large step by enabling systems to directly share each other's main memory. Full hardware load store access to the other guy's memory as if it was in your own computer. Latency? Roughly only 50 to 100 nanoseconds worse than a remote socket in your own system. Good enough to still be used as main tier memory. How might this be used? Well, consider a pod of 8 2-socket servers, each with 8 terabytes of memory. Imagine 3 premium workloads, each consuming the compute resources of a server, but with differing memory requirements. While workload A could run happily without a memory clustering capability, look at workloads B and C. They both need 3 times more memory than a single box can provide. By borrowing from their neighbors, their needs are met. Fundamentally, we can cut memory costs since we don't need to configure each server to meet spike demand. But this is a small example. With Power10's 2 petabyte physical address range, we can think big. How about instead of clustering 8 small systems, why not use the biggest, baddest 16 socket systems? And why stop at 8 of them? Why not pull together all 2 petabytes worth of shareable capacity? Or consider a hub and spoke topology. Maybe a large system maxed out on memory and several small, dense, inexpensive servers without any memory at all, borrowing from the mothership. There are lots of possibilities. Instead of just sharing with your neighbor, why not build messaging software? Right to the memory that lives across the data center by retranslating addresses at every hop, using page tables as routing tables, using 2 petabyte addressability for routing IDs, and incorporating robust virtual channel management. A fully hardware-managed end-to-end messaging capability is possible. Thousands of nodes, flexible topologies, robust bisection bandwidth, low latency, cables only, no extra gear. Memory inception for pod-level memory resource pooling or for clustering up to thousands of nodes without any extra gear. Power10 opens the door to memory disaggregation, transforming cloud infrastructure economics. Last, but certainly not least, Power10 incorporates high bandwidth benefits of PCI Gen 5 and the breadth of the PCI ecosystem, up to 64 lanes per socket in the dual chip module offering. Before handing this over, I want to share a performance analysis of a Power10 dual socket system compared to its direct Power9 predecessor, a Power9 S924 system. 3x performance relative to Power9. That is an outsized gain for one generation, our strongest in over a decade. And for memory, we see the positive impact of OMI. Brian, our chief core architect, will walk through the IPC and energy efficiency details underneath those integer, commercial enterprise, and floating point gains. And just wait till he shows you the larger gains for AI inference. Brian, take it away.
Thank you, Bill. I'm Brian Thompto, and I'm excited to share with you many of the innovations and capabilities of our Power10 processor core that help make Power10 ideally suited for mission-critical applications and the opportunities of the enterprise cloud. The Power10 core was focused first and foremost with providing gains in performance while at the same time reducing the energy consumption required. This resulted in a new microarchitecture that delivers extraordinary generational gains in computational efficiency. Compared with Power9, the Power10 core delivers an average of 30% performance improvement across a range of workloads and 20% gains for single thread. Combined with a ground-up focus on energy efficiency, the Power10 core provides a 2.6x improvement in performance per watt. At the socket level, these efficiency gains are further amplified as we're able to pack in significantly more cores in our DCM socket and operate at a more efficient operating point, delivering 3x improvements in performance and efficiency. Using the same modular building block concepts as Power9, the Power10 core provides deployment flexibility, supporting up to 8 threads and providing for a second chip variation with 4 threads per core and twice as many cores. That is, up to 30 big SMT8 cores or 60 SMT4 cores per socket. A second major focus for the new Power10 design was to supercharge the processing core to accelerate AI, enabling infusion into the enterprise applications. As seen in the core die photo, these capabilities were built into every layer of the design: cache, load store, SIMD, and the introduction of a matrix math accelerator providing 4x throughput gains versus Power9. We'll go into each of these themes a little deeper in the remainder of this presentation. As depicted on the right side of this diagram, the modular Power10 core provides enterprise flexibility and supports from 1 to 8 active threads with an optimized balance of resource sharing, isolation, and efficiency. This flexibility extends to supporting a world-class set of software stacks, including AIX, IBM I, Enterprise Linux, and container-based stacks including OpenShift, all designed to run side by side in the same socket with the PowerVM hypervisor. Power10 extends this flexibility by supporting the KVM hypervisor running on top of PowerVM as a high-performance nested hypervisor. This opens the door to additional deployment flexibility for KVM and supports enhanced security. Enabling a host of new capabilities in the processor core and system, Power10 implements the Power ISA version 3.1. The new ISA was also contributed to the Open Power Foundation and extends Power's commitment to open communities and supporting an open development ecosystem. The new ISA supports 64-bit prefix instructions in a RISC-friendly way in addition to classic 32-bit instruction forms. This adds new capabilities to existing instructions, such as PC relative addressing, as well as providing a rich new opcode space ready for future expansion. Power10 supports over 200 new instructions, including 32-byte loads and stores, and new AI accelerating instructions and data types. It also adds a number of advanced system capabilities designed for the connected cloud with enablement for the Swiss Army knife of Power10 connectivity that Bill showed us, including memory inception, advanced storage optimizations and memory tiers, as well as enhanced security measures. Enterprise-grade security requires delivering on security across the software stacks. The Power10 processor builds on a strong foundation of security and isolation, co-optimized from the hardware through each secure virtualization layer and the application layers, as depicted in the right side of this chart. Confidential computing capabilities are enhanced in Power10, enabling the deployment of secure containers in the enterprise cloud. In this co-engineered approach between hardware and the Power VM hypervisor, secure containers are isolated and protected from threads in the application and virtualization layers, allowing Power10 to extend the traditional level of platform security to the latest cloud-oriented software and frameworks. Power10 also includes full and transparent memory encryption, providing additional security in the cloud data center. Applications on Power10 can also take advantage of higher performance core cryptography and active management measures in the processor core to provide enhanced performance while retaining robust side channel avoidance. Now, let's take a deeper look at the performance and efficiency foundations of the Power10 core. Depicted in this chart is a block diagram showing the high-level core microarchitecture for Power10. The resources shown support between 1 and 4 threads, one half of the SMTA core. Instructions are fetched from the L2 cache, the lower right, up through the predecode and into the level 1 instruction cache. Power10 then decodes and dispatches instructions to the execution slices at up to 8 instructions per thread and 16 per SMTA core. The execution slices on Power10 are each double the width of Power9, each able to do a 128-bit SIMD operation per cycle, and each with fixed, float, permute, and crypto capabilities. The core also includes matrix math acceleration engines, providing a 4x growth in flops and AI data type support. Power10 supports significantly larger working sets, including 4 times the L2 capacity, 4 times the TLB capacity, and a 50% larger instruction cache. Power10 also supports deeper instruction windows, larger queues, with up to 1,000 instructions in flight per SMT8 core. Data latency access was also reduced. L1 data store forwarding is performed with a nominal low-to-use latency of 4 cycles, eliminating 2 cycles and associated pipeline disruptions. Access to L2, L3, and TLB were also reduced. 2 cycles less for L2 cache and 8 cycles less for the L3. For branches, we doubled the BHT predictor and have included new tag predictors for both indirect and relative branches. We also made a significant change to branch execution, merging the branch pipeline into the execution slices and targets into the main register files. This reduces latency and improves efficiency. We leveraged the new prefix instruction detection circuitry in the predecode to also identify instruction fusion opportunities. Power10 supports a wide array of fusion sequences, including scalar and SIMD instructions, eliminating dependencies, as well as supporting fusion between consecutive loads or stores, utilizing each of the wider load and store pipes to handle 2 instructions at once. Combined with store gathering in the core, each store port to the L2 can drain up to 4 stores per cycle. So, a lot of changes for performance, but to accomplish our goals for Power10, we had to redesign from day one for efficiency. This included deployment of enhanced tools, physical design techniques, and innovations in the microarchitecture. Each design element was re-examined to improve clock gating and reduce switching capacitance. Many of the improvements for performance also paid double dividends in efficiency by reducing wasted work. In addition, we benefited from redesigning major structures, such as queues and register files, with a focus on port reduction. That included changing our level 1 data and instruction cache structures to be EA tagged. This allows instructions to flow through the pipeline without the need to perform address translation. The ERAT, for example, is only accessed on a cache miss, and tracking structures took advantage of simpler tagging to improve efficiency. All of this redesign and innovation result in significant improvements in both performance and performance per watt. The Power10 core achieves 30% improvement in IPC while consuming 1/2 the power, a 2.6x improvement in core efficiency compared with Power9. At the socket level, this adds up to an aggregate of 3x improvement at a more efficient operating point, and as Bill showed, also translates into 3x performance. The Power10 core supports the seamless integration of AI in the enterprise cloud. Our AI focus is partly about the compute, but it's also about the data. Machine learning algorithms depend on the ability to move and prepare data and feed computations effectively. So Power10 also focused on something a little more traditional to computing, providing robust bytes per flop. Moving from Power9 to Power10, we doubled the ability to bring in data from every level of cache and from memory to the compute engines. That is, 2x from the L1 cache enabled by wider load and store instructions and fusion, up to 4 32-byte loads or 2 32-byte stores per cycle per SMT core. As AI inference goes to work in the enterprise cloud, individual cores can also be central to data ingestion or for feeding transactional inference. So we plumbed in 2x bandwidth from memory through to the cores, and we can sustain a rate of 120 gigabytes per second out of a 256 gigabyte per second peak read plus write with a single SMT8 core. That's 2x on the byte side of our story. Now let's look at the flops. We doubled our SIMD engines to 8 per SMT8 core to provide bandwidth matched compute and tackle data preparation as well as a host of machine learning algorithms. We did this while staying within our existing 128-bit SIMD register architecture, providing flexibility to software while boosting the performance in existing binaries. We also focused on algorithms that were hungry for flops, such as the matrix math utilized in deep learning. Every core has built-in matrix math acceleration that efficiently perform matrix outer product operations. These operations were optimized across a wide range of data types, recognizing that various precisions can be best suited for specific machine learning algorithms. We included very broad support: double precision, single precision, 2 flavors of half precision, including both IEEE and bfloat16, as well as reduced precision integer, 16, 8, and 4-bit. The result is 64 flops per cycle of double precision and up to 1K ops per cycle of reduced precision math per SMT8 core. These operations were tailor-made to be efficient while applying to machine learning. The reduced precision operations accumulate into 32-bit results, preserving precision and reducing algorithmic overhead. You can see one of these MMA operations depicted in the upper right. This efficient matrix math that is performed is based on just 128-bit operands, 2 of them, and accumulate into a 512-bit result register. Per SMT8 core, we can do 4 of these operations per cycle. Just as for the main SIMD engines, the new matrix math acceleration doesn't require any new architected register state and minimizes software ecosystem disruption. It also enables performance for machine learning frameworks and applications to be employed by simply updating libraries in many cases. Re-referencing the die photo in the lower right, all of that matrix math happens in the blue rectangle on the right side. With a purpose-built structure that leverages data reuse efficiency, the accumulated result data is stored local to the computation, while operands are streamed in from the cache hierarchy for 2x efficiency versus traditional SIMD. These operations provide 4x plus throughput per core and also significantly reduce latency. A 3 times inference latency reduction for a single thread using single precision, and a 6 times reduction in latency for integer 8. At the socket level, you get 10 times the performance per socket for double and single precision, and using reduced precision, bfloat16 is sped up to over 15x, and int8 inference sped up to over 20x versus Power9. This gives Power10 the AI horsepower to integrate AI intelligence in enterprise applications. Now, let's review how the main technology themes of Power10 provide extraordinary capability for the enterprise cloud, whether on-prem, public, or hybrid. A robust data plane enables the most resilient, scalable SMP servers, and provides unparalleled flexibility for deploying workloads in the enterprise clouds of today and tomorrow. A new enterprise core provides significant performance and efficiency gains and was co-optimized to run flexibly with world-class software stacks. Security was engineered across the stack to provide enterprise asset protection to the latest class of cloud deployment scenarios and software, and extreme generational gains of 3x performance and efficiency improve computational capacity across a broad range of workloads. Finally, in-core, accelerated support for AI inference provides 10 to 20x generational speedups to power AI infusion into enterprise application workflows. These demonstrate how Power10 was truly built for the enterprise cloud. Before we conclude, we'd like to acknowledge the Samsung Foundry as a stellar technology partner for Power10 and extend a big thank you from our amazing Power10 development team to this worldwide Hot Chips audience.
Thank you, Bill and Brian. So here are some questions, and let me start with the very first question that was asked a few times. Just read it and you can then answer. With PCI Gen 6 spec targeted for release in 2021 and devices in market by 2022, what is the potential that future Power10 CPUs will be updated to include this? It's stated that Power10 systems will be shipping in late 2021. Will we have to wait for PCI 6 in Power 11?
So yeah, we're not going to talk too much about what we're doing in the future right now with any Power10 derivatives or things we might call Power 11. We're really only here to talk about Power10 now. As I mentioned, actually in the Slack earlier, PCI, it's been great to see. It's moving at a faster rate. For a while there, it seemed to kind of slow down. So as Gen 5 matures, Gen 6 comes in, we're always going to be looking at, what are the market conditions, where does it look like adoption is going to be, and we'll be making decisions on when we offer it. But that's all I'm going to say on that one.
Next question. How much does read latency increase with the serial OMI interface plus media controller on the OMI DIMM?
So I want to make sure I understand the question. I think you're asking, so this would be for a standard like DRAM based memory using OMI instead of a direct attach. It's like less than 10 nanoseconds of additional latency for a main tier memory, if that's what the question was. Did I get that right?
It came off Slack, so that's what it says. So maybe on the Slack you can further ask them to explain it.
Sure, and by the way, we're seeing a lot of questions on Slack, and we've already answered a few of them. We're going to do our best over the next day or so to get answers to all those. So thanks for everybody for asking all those great questions.
Fantastic. So let's now do last two questions, then we can move on. So did power delivery get upgraded as well? Are you still relying on die LDOs?
Yeah, so
go ahead, Brian.
No, I mean, so in general, there were a lot of improvements to power efficiency, but the overall method of doing power delivery is something that we'll go into many more details like in ISSCC. So we don't have a lot of details to share here. Nothing significant at an architectural level. We're still on the same power delivery platform as we were on Power 9.
Okay, so the next question. Now let's talk about, you had significant power performance efficiency improvement. What was the single most important factor? If you can at least share some little bit more detail.
Yeah, there were really many factors here. So there's no one single element. I think it garbled a little bit. I think the question was about power performance improvement and what were the main factors. Did I get that right?
Improve energy efficiency, yeah.
Yes, absolutely. So it really took many fronts, right? Many factors. So as we described, right, a lot of this was through redesign. So we really did microarchitect from the ground up in the processor core. That was microarchitecture. Those were many tools and physical design techniques, as well as at the socket level, really taking into account from day one our energy efficiency goals and the ability to have that dual chip module and enable all of those cores packed into one socket, right? So all of that from day one. And of course, the 7 nanometer technology from Samsung was also a part of that. So it really was all of that coming together to let us engineer for that significant improvement that we got.
Okay, good. We have another IBM talk coming up, so let me ask you one more question. IBM is presenting 2 papers in this session. Do you guys work together, the mainframe guys and power processor power guys like you all?
Yeah, all the time. We're continually peer reviewing each other's work. We do get a lot of questions on why the architectures are so radically different, and that is because they are both very well suited to the different sorts of client bases and operations that we're running. And so there is good justification for a pretty wide variation in what we do. But the beautiful thing is we both become kind of experts in each other's space by doing all the peer review. And there's a lot of cross-pollination, a lot of ideas go back and forth. And then also IP sharing, the OMI memory, that we talk about, or in the past, the CDIM-based memory that we talked about, that's kind of a shared feature going across platforms, as well as many other shared features that we can pick up on, a lot of the physical things like that. So really great synergy between the two platforms, but also a lot of differences between them.
Okay, beautiful. So that's all the time we have. Thank you again. Audience, you can clap as well there on the Slack channel if you want. Thank you. Now we move on to the third talk in this session. Third talk will be Marvell Thunder X3 and speaker is Rabin Sugumar. Rabin is the chief architect at Marvell and leads the architecture group for the Thunder X3 server processor series. In his role, he participates in a variety of aspects of Thunder X development and productization. Rabin joined Marvell from KVM, which was acquired by Marvell in 2018. Prior to this, he was at Broadcom, where he was one of the lead architects on the server processor that later became Thunder X2 when the team from Broadcom moved to KVM. During Rabin's career, he has worked on architecture and design of vector processors at Cray Research and early multi-threaded out-of-order Spark processors at Sun and ARM-based processors at Broadcom, KVM, and now Marvell. So you can see he has a very broad experience in Silicon Valley. He obtained his PhD from University of Michigan, where he did research on simulation techniques, and similar to that Rabin developed during this tenure at there known as Cheetah, is still used worldwide in academia. So with that, let's get, Rabin, please get started.
Thank you to Pradeep for introducing me. I'm excited to be here at this virtual forum talking about Thunder X3, the next generation server chip from Marvell based on the ARM instruction set architecture. Let me start out by acknowledging the many talented people who have worked on this project through the years and brought it to this level. An amazing amount of work has gone into making this chip a reality. In this talk, I will start with a brief overview of Thunder X2 and Marvell's Thunder X line overall. And then we'll dive right into the architecture of Thunder X3, going into some detail on the core, the threading, and the memory subsystem architectures. I'll also show some performance data from Thunder X3 silicon. For those who are not familiar, Thunder X3 will sell into the server market, basically the same market as server chips from Intel and AMD that are being presented here. Going on to the next slide. The chip prior to Thunder X3 was Thunder X2. For those who have not heard of it, it is a 32-core die. Each core had 4 threads, so there were 128 hardware threads presented to the OS as 128 CPUs. It implemented ARM v8.1. Thunder X2 has several firsts to its credit. It was the first ARM-based system in the supercomputing top 500 list. It came up to 161, I think. It's also the first non-x86 CPU in Microsoft Azure. It is the most widely deployed ARM server processor currently. At the time it came out, it had industry-leading performance, especially on bandwidth-intensive benchmarks and applications. And over the last 2 years, we have qualified the chip at data centers and have fixed a variety of issues in the process. And Thunder X3 is an evolutionary build on top of that and leverages many of the learnings. This chart shows the Marvell server processor roadmap. Thunder X, the first chip in the line, came out in 2016. And then Thunder X2, which we just talked about briefly, GA'd in 2018. This talk is about Thunder X3, which is sampling now. There are two variants. There is a single die variant with 60 cores and a dual die variant with 96 cores. And the design team is busy working on Thunder X4. This is a brief overview of Thunder X3 before we get into details of the architecture. As I said, the single die has 60 cores and the dual die goes up to 96 cores. It implements ARM version 8.3, pulling in select version 8.4 and version 8.5 features. It has 8 DDR channels, DDR4 channels going up to 3200. And it has 64 PCIe Gen 4 lanes. It has a sophisticated on-die power monitoring and power management subsystem. It also has SATA and USB interfaces on the die. On performance, we see about 30% over Thunder X2 on single thread spec int, even more on spec FP, and significantly more on data center codes. On a single die, on a variety of workloads and applications, we see 2x to 3x over Thunder X2. We expect when Thunder X3 is released, it'll be industry leading on performance. This shows the Thunder X3 core block diagram. I will walk through the pipeline here, and then subsequent slides get into a little bit more detail on subcomponents of the pipeline. So fetch is when we read instructions from the instruction cache. The instruction cache is 64 kilobytes. We read up to 8 instructions a cycle. Along with instruction cache access, branch predictors are access to. We have large conditional and indirect branches predictors and retire and return predictors. The fetched instructions go into decode. Decode is 8 wide as well, and decode maps instructions to micro-ops. Most instructions map to a single micro-op. But there are a few instructions that map to more than one micro-op. Out of decode, the micro-ops go into a structure that we call the skid buffer. That's the boundary between the front end of the pipeline and the back end of the pipeline. This is one of the few structures that are actually private to each thread. So each thread has its own copy of the skid buffer. Pretty much most other structures are shared by all the threads. The skid buffer is also where the loop buffer is located. So when a loop fits in the skid buffer, we are able to dispatch right from the skid buffer without having to fetch instructions from the instruction cache and decode them. So from the skid buffer, UOPs are taken out and then they are renamed and dispatched to the scheduler. The max dispatch rate is 4 micro-ops per cycle. The scheduler is unified and it's 70 entries deep, and it feeds out to 7 ports. 4 of the ports are arithmetic, so they are shared by the integer ALUs and the floating point neon units. 2 of the ports are the load store address units, and there is 1 store data unit as well. The L1D cache is 32 kilobytes, and both the instructions and the data share a 512 kilobyte unified L2 cache. The prefetcher is located, the hardware prefetcher is located at the L2 cache and fetches into the L2 cache. So going to the next slide and a little bit more detail on fetch. We spoke about many of the details here. So it is 64 kilobyte iCache. One feature to highlight here is decoupled fetch. This is an enhancement over Thunder X2. We found that data center codes miss a lot in the instruction cache, and in some cases, even in the L2 cache, the instruction side in the L2 cache. And with decoupled fetch, we are able to walk down the predicted path using a large BTB and keep fetching subsequent cache lines while we are waiting on the first miss to be satisfied. So it actually helps performance significantly on many data center codes. And as I said, decode breaks a few instructions into multiple micro-ops. So from decode, we go into the skid buffer. The skid buffer is partitioned among the threads. Couple of things to note here. No ops are not dispatched to the scheduler. They just go to the reorder buffer and retire. And one of the challenges with pipeline design is with the branchy code, instruction bundles get very short. And in the rename stage, we try to merge bundles from adjacent entries in the skid buffer to create larger dispatch groups, which helps performance in many cases. Going on to the scheduler, this shows the 70-entry unified scheduler and the integer and FP ports that it feeds to. And one thing to highlight here are the depths of the different out-of-order structures, quite deep. And then finally, the data cache, the TLB, and the L2 cache, which is actually unified, but we put it here. We talked about many of these things. The L1 TLBs allow zero cycle, zero impact translation when pages hit in the L1 TLB. And the hardware prefetcher does next line, strides, and also region. And it's quite effective at bringing in cache lines for future use. So for a 30% performance improvement, a number of dimensions have to be addressed. SpecInt is actually quite a complex benchmark if you include all the components, and to get 30% over a geometric mean, a lot of dimensions have to be accessed. So this kind of lists the main focuses of the design. So that is the size, that is the width, that is the algorithms, and then the latency itself. To call out a couple of highlights, the larger out-of-order structures help significantly. So this is the scheduler itself, the reorder buffer, the load and store queues, and related structures. And another highlight is the micro-op expansion. Owing to the history of Thunder X2, we expanded micro-ops probably more than ideal on Thunder X2, and we fixed many of those issues on Thunder X3 and got a big gain there. This shows early performance measurements from Thunder X3 silicon. On SpecInt, it's a 1.5x gain approximately. 30% is from architectural performance gains, and then so the rest is through the frequency increase over Thunder X2. And then on SpecInt rate, owing to the larger core count, the architectural performance increase, and the frequency increase, we get close to 2.5x over Thunder X2. Spec-FP, we actually see a slightly higher gain than on SpecInt. And on data center codes, depending on the benchmark, we see anywhere from 2x to 3x. It's still early, but on FP, for instance, even in the couple of weeks since these slides were prepared, the gains have gone up a little bit. So we will dive a little bit into multi-thread execution in this slide. So there are 4 hardware threads per core. Each thread includes a full copy of the ARM architecture state. So as far as the OS is concerned, each thread is a full CPU. The threads share all pipeline resources. So So the execution units, the cache hierarchy, the interfaces, the various structures like the reorder buffer, the scheduler. Yeah. So the design has always been multi-threaded, but we did do a what-if study once to see what the area impact is, and should be taken with a grain of salt, but it's about 5%. So it's a pretty efficient feature. This slide talks a little bit about how thread arbitration is done. There are 4 points of arbitration. At fetch, the thread with the least instructions further down the pipe is picked for fetching. So this ensures that the number of micro-ops and instructions further down the pipe are balanced among the threads as far as possible. At rename, similarly, when threads are picked for dispatch out of the skid buffer, the thread with fewest instructions further down the pipe is given priority. In the scheduler, there is no notion of threads. It just picks the micro-op that is oldest. And the execution units are also thread agnostic. And then finally at retire, the thread that has the most micro-ops to retire is picked with a mechanism to avoid starvation. We find that the arbitration works well on most codes. When we run the same code on all the threads, the execution latencies are quite uniform. A little bit on threading performance. The speed up from threads tends to be correlated with the IPC. The lower the IPC, the more the speed up, because there is more slack to hide. We see that for something like MySQL and many other data center codes where the IPC is low, the speed up is quite significant. So we see more than 2x going to 4 threads. And then for something like Leela, where the IPC is mid-range in the 1.5x-ish range, there is still good gain, 1.7 plus x on 4 threads. And then with high IPC codes like X264, which is the video encoder from spec, it's about 28%. So it's still not insignificant. And then at the socket level, this is MySQL. So we have a MySQL server running, and then we increase the number of client threads. And we see that there's a linear region where new cores are coming in. And then there is a threading region which flattens out a little bit, but still quite good gains. And then after 240 threads, which is the total number of hardware threads on a die, it flattens out. And we get a net 89x over a single thread, which is quite significant. A little bit on the L3 cache and the interconnect. We have a switch ring interconnect. The cores and L3 caches are columns, 3 columns with a switch at the top. And then when a traffic needs to go from one column to the other, they go to the top or bottom switch and then get switched to the column they need to go to. There is no notion of locality for the L3 cache. It's cache line striped. It's logically shared and physically distributed. It's a 90 megabyte cache, so this architecture allows large data structures to be held in the L3 cache, and there is no duplication. It's filled on evictions from L2 cache, and it tries to be exclusive. This also increases the effectiveness of on-die SRAM. We implement Snoop-based coherence with Snoop filters to reduce snooping traffic. So Thunder X3 is a significant upgrade over Thunder X2. We see on many codes up to 3x over Thunder X2, which was industry leading when it came out. It took an evolutionary design approach. It leverages the Thunder X2 platform as much as possible. And we expect that it will get to production quality quickly. The 4-way threading provides significant performance advantage on many data center codes over competitor systems. And Marvell has a strong tradition of processor design. and a strong roadmap in the server line coming up. Thank you. Also increases the effectiveness of on-die SRAM. We implement slope-based coherence with slope filters to reduce slope parameter. So ThunderX3 is a significant upgrade over ThunderX2.
Our question is, who's manufacturing it?
Should I answer that?
Up to you.
Okay, so I'm live then. Okay, so this chip is being manufactured by TSMC in their 7-nanometer process.
There is no SVE.
Yeah, there is no SVE on this chip. Partly it didn't line up with our development schedules. Also, it seemed like a better fit for the next generation ThunderX chip. So yeah, it is coming in the next generation, but we decided not to support it in this generation.
Okay. So as you know, there are multiple server processor vendors now, right? So can you, would be possible for you to, you didn't offer any comparative comparison, but if at least it's something that you're able to share, in what specific areas does your chip stand out compared to Intel, IBM, or let's say even Amazon?
Sure. So let me kind of give a broad overview, right? So versus Intel, on single thread, Intel actually turbos to high frequencies. So even though on a per gigahertz basis, ThunderX3 is faster, overall on a single thread level, Intel tends to be faster. However, Intel chips seem to have a lower core count. And so on throughput, so if you look at spec-int rate or data center benchmarks, ThunderX3 is actually significantly higher than Intel. If you go to AMD, it's kind of, I would say, a little bit of a reverse. Their single thread performance is a little bit lower. So ThunderX3 actually does better than AMD on single thread. And then on throughput, on like rate types benchmarks where there isn't that much sharing, AMD is a very good chip because with their chiplet architecture, they're able to pack a lot of cache and a lot of cores. But then when it comes to codes with more sharing where there are producers and consumers and data has to move from one cache to the other, the scaling seems to drop. So on database codes, we do see significant performance gains for ThunderX3 over AMD. And then for Graviton 2, which is another competitor from ARM, that's a really good chip. I would say that they don't have threading. Their frequency is a little bit lower. So both on single thread and on RAID, they're a little bit behind, but it's a good chip with a lot of potential.
Oh, very good. Okay, yeah, thanks for answering this in quite some detail, and it's very good. Thank you. Moving on to the next question. Why did you, related to your network on chip, why did you choose switched ring interconnect topology versus mesh or just a single ring?
Yeah, so it was kind of a trade-off between the design changes we wanted to make, the area impact, and the performance we needed. So on ThunderX2, we had a simple ring, and extending the simple ring to ThunderX3 became problematic because we had to fit a lot more cores on the ring. Going to a full mesh would have been a bigger design change, and it didn't seem necessary. And the area impact of all the mesh links would have also been, we had to reduce the number of cores we supported. So the switch ring, where we added one more column in the middle and then added a switch at the top and bottom to go from one leg to the other legs, seemed a bit good trade-off. One of the metrics we use to evaluate our interconnect bandwidth is how much we get on stream running out of the L3 cache. So stream is a benchmark that people use for memory bandwidth, but by constraining the size of the arrays, you can actually make it run out of L3 cache. And on stream running out of L3, on ThunderX3, we see 15% more bandwidth per core than Thunder X2. So even though we have almost double the number of cores going from Thunder X2 to Thunder X3, on stream, we still see a 50% per core bandwidth improvement. So the interconnect bandwidth is pretty good on Thunder X3.
Thank you. That's all the time we have. Thanks again, Rabin, and continue to ask questions, audience, please, in your Slack channel.
Yeah, please. And we also have a Marvell Slack channel, so do interact with us there as well. Thanks.
So moving on to our next speaker. Next speaker is closing again the session with an IBM talk. We started with an Intel talk, IBM, Marvell, and now again last talk is the Big Iron mainframe. Anthony Saporito is our speaker. Anthony works at IBM Systems Division in Poughkeepsie, and he's a senior technical staff member at IBM Systems Group. He joined IBM in 2001 after his bachelor's degree in bachelor's in electrical and computer engineering from NJIT, New Jersey Institute. He received a master's from Walden University while working at IBM. He was the lead architect for the recent Z system microprocessor and has contributed to several generations of Power and Z system with a focus on branch prediction, instruction fetching, and cache design. He's currently focused on AI acceleration and deployment for future system design. He holds over 150 patents and has been named IBM Master Inventor. So Anthony, take it over.
Most people know the word mainframe, but they think of them as stuff from movies or old room-filling computers from prior generations. I'll offer a few words about their history and how relevant they still are in our daily lives. The mainframe was actually the first system to introduce the concept of architecture separate from a specific implementation. That allowed different designs and generations to comply with and maintain software compatibility with prior generations. What that means is software and compilers didn't have to be rewritten for every new machine that came out. Now that concept is totally commonplace now, but it wasn't always that way, and that was brought to you by the mainframe. And by the way, programs that were written for the first generation mainframe back in 1964 still run just fine on our current models. Many of us learned of Tomasulo's algorithm back in school, and that concept is the basis for out-of-order execution that's present in nearly all modern CPU designs. Robert Tomasulo was a mainframe engineer many years ago, and his famous algorithm was designed into the floating point unit of the 1967 Model 91 mainframe. Okay, onto some of the stats on this page. I like this first one because it's really tangible. We all use Google to do internet searching, some of us a little bit and some more than others. The entire world population right now is close to 8 billion people, and all of those people combined generate around 70,000 searches per second. Compare that to 1.3 million CICS transactions that are processed every day in the same amount of time on mainframes. Most of us use the mainframe today without knowing it. When you swipe your credit card to make a payment, your transaction likely went through a mainframe. If you checked your book airline reservations, it almost definitely went through a mainframe. If you take money out of the ATM, same thing. So when most of us hear COBOL, we think of a really old programming language that no one codes in or uses anymore. But it turns out there's actually a whole lot of COBOL that's still running mission-critical applications out there. Over 220 billion lines of it are still in use, and that code accounts for around 70% of the world's business transactions. That's why we still invest a lot of energy and CPU design to make that code run faster on our machines. Today I'll talk about the chipset used in our latest Z15 offering and a little bit about the overall system. This chart's a bit of a refresher on the prior 5 generations that came before Z15. They're all part of a family of deeply pipelined, high-frequency designs. Back on Z196, we reintroduced out-of-order execution to the mainframe. The ZEC12 was the first commercially available platform that supported hardware-based transactional memory, and on Z13 we introduced dynamic simultaneous multithreading. Z14 had a system feature called pervasive encryption that was made possible by fast on-core cryptographic acceleration. And for Z15, well, I'll spend the rest of the time here talking about some of the latest features that we built into this. So one thing to note, the CPUs that power the Z system machines are ground up and custom built by us. They're not used in any other product lines or computers. This chart shows an overview of the system and draw level design and how things are connected up. So there's actually 2 different chips in the chipset for Z15, the SC and the CP. The CP chips contain the processor cores, a large L3 cache shared amongst them, and things like on-chip accelerators and memory and I/O interfaces. The storage controller or SC chip contains a large 960 megabyte L4 cache, and it interconnects the two CP clusters on either side of the draw. It also connects up all other draws in the system through the green cable shown in the depiction on the top left here. The diagram on the top right shows how 5 draws in a fully populated system are interconnected, fully connected between each other through the SC chip. So the CP and SC chips are both large 14 nanometer SOI designs coming in at around 700 square millimeters each. The CP chip weighs in at over 9 billion transistors and the SC chip at over 12 billion, both using 17 layers of metal. The CP chip has 12 cores on it, and each of them has a private 4 megabyte L2I cache and a private 4 megabyte L2D cache. On the chip is a shared level 3 256 meg cache. So the max configuration contains up to 20 CP sockets across 5 draws, and that gives 240 physical cores. 190 of those are customer configurable, and the remaining ones are used either as system assist processors or spare cores that are able to dynamically come online and replace others that encounter non-recoverable hard faults. And I'll talk a little more about that later. So the system supports a max of 40 terabytes of main memory, and that's 8 terabytes per draw, and up to 192 cards that provide 384 channels of I/O. On the bottom right, you can see a max 4-frame system. So these come in either 1, 2, 3, or 4-frame options. And they're industry standard 19-inch frames. And this shows a full 5 CP draws. And then the remaining draws in there are for power and cooling and a lot of I/O. Zooming in a bit, you can see the actual layout of a single CPC draw here. On the very top are all the PCI connections, and just below that, you can see the single air-cooled SC chip. Continuing down, there's the 2 clusters containing the 4 CP chips that are under cold plates, and below that are the 20 memory DIMMs that can give you up to 8 terabytes per draw. And finally, at the very bottom are the cooling fans. So this is what's listed as the front, and that's what you would see if you were standing in front of one of the main frames and opened up the front draws. This page gives a high-level design summary for what went into the Z15 processor compared to its predecessor. So things here are broken down into 3 major categories, and the first one's classic microarchitectural innovations. And these provide what I call behind-the-scenes improvements, and that means that applications benefit from them and they run faster without requiring any changes, modifications, or recompilation. So on the bottom right, you can see a blow-up of a single CP chips layout, and there's 12 cores on here running at 5.2 gigahertz, and you can see 6 of them on each side of the chip. So each core has a private 128K level 1 IND cache and a private 4 megabyte level 2 IND cache. In the center, you can see that honking large 256 meg level 3 cache that is shared by all the cores on the chip. And around the edges of the chip are things like the memory controllers, I/O, accelerators, and the interfaces to the SC chip and the other CP chips in the cluster. The second category shows some of the updates that we've made to the ISA. These additions support new features like accelerators and secure execution, which I'll talk more about later. We also added close to 40 new instructions that target speeding up frequently used operations in a more direct way. The final category shows how we invested heavily in a mixture of accelerators that are either built directly into every core or shared at the chip level. So these provide the backbone of some of the system's new features and functions like compression acceleration, elliptic curve cryptography, and sorting and merging. I'll dive into more of the details on the ECC and compression accelerator in just a bit. So we set out with the pretty lofty design goal of staying in the same technology node, but figuring out how to stuff 2 more cores and much larger caches and structures onto a chip without growing that chip. So you can see here that several of the structures grew by 20% or more, and we doubled the size of things like the L3 cache, L2I cache, and the level 1 branch predictor. The out-of-order register renaming mapper was redesigned to be more area and power efficient, and it landed with twice the number of entries and about half the size of its predecessor. The effect of all these improvements nets an average of 14% single-threaded performance boost over our prior design. Here's a very brief review of our overall pipeline, which is deep to support running at 5.2 gigahertz. The instruction set is a rich CISC architecture where complex operations are cracked into simpler micro-ops and scheduled for execution. Branch prediction runs asynchronously and often well ahead of I-fetching, and it acts as a really good I-prefetcher. Instruction fetching, parsing, decoding, and grouping, and dispatch all occur at the front end of the pipe in order. The execution pipes are shown here in the green box, and they all run out of order. The diagram shows some detail in each of the pipes, but there's actually 2 copies of pretty much everything shown here. On the back end, groups of instructions complete in order, and there's a robust recovery unit that maintains the golden architected state of the processor, accounting for the last set of instructions that completed error-free. In the event that an error is detected, the processor rolls itself back to the last known good state and resumes execution. This allows for seamless recovery from transient errors. A large investment in error detection circuits combined with this rollback recovery feature allows these chips to continue executing programs without a hiccup, even when we intentionally blast them with high-energy proton beams and alpha particles under test. In the extremely rare case of a non-transient hardware fault, the known good state can be quickly transported from a failed core to a known good spare completely under the covers and without any running programs or applications stopping or even noticing. For a number of years, we've had a PCI-attached accelerator for compression that was zlib gzip compatible. On Z15, we've moved the function right onto the processor chip, giving it much higher bandwidths and greatly reduced latencies for starting and stopping the accelerator. This ultimately allows for improved use cases where you could use the accelerator for smaller blocks since the overhead is that much smaller. Additionally, the accelerator is a lot faster since it's on the chip and it runs at processor frequency. That's compared to the prior card accelerator, which was an FPGA implementation and it ran only at a few hundred megahertz. These two features combine for a drastically improved application space for compression acceleration. The new accelerator fetches from and stores directly into the on-chip shared L3 cache, but it's also tightly integrated with the cores. We introduced a new non-privileged instruction to use the accelerator that invokes what we call MIDI code, and that's a form of firmware that runs directly on the processors. So this firmware handles the prefetching of the data that the accelerator will use into the L3 cache on the chip. It also handles things like dynamic address translations and most of the exception testing for the accelerator. The firmware will invoke the accelerator and push all the translated addresses that it's going to need for fetching and storing directly into queues on it. And the accelerator during operation will read from these queues and take the addresses to do the fetching and storing right from the L3 cache. As the accelerator is working, the firmware running on the core races ahead to prefetch and translate the next set of addresses it will need. The two communicate throughout the entire operation to keep the input and output queues full and the required data hitting in the cache. This is a synchronous operation that runs in real time. Let's dive into a little bit of how this actually works and what's under the accelerator's hood. So here's one of the cool ways that we enabled speed, physical design efficiency, and a high compression ratio. Traditional compression engine designs typically either use a CAM-based approach or an SRAM-based hash table as a dictionary. There's pros and cons to both of these solutions. So CAM designs provide really high matching accuracies and great compression ratios, but they're real hogs physically. And that's because all of the stored bits have their own compare circuitry for matching against the input. On the other hand, SRAM-based hash tables are much more area and power efficient since they're built from simple, dense storage cells. But the limited array access ports, bank collisions, and hashing limitations all reduce the precision, and that lowers the resulting compression ratio. In this algorithm, the window size refers to how far back you look at the prior data you encoded to find patterns you could use to compress the current data. While a larger window size gives a better compression ratio, we realize that the data closest to what you are currently compressing has the biggest effect, and that impact trails off the further out you go. This led us to a hybrid design approach where we use a CAM for the most important 512-byte near history and a less precise but area-efficient hash table for the far history, the far history being 513 bytes all the way out to 32 kilobytes. Given our area and timing budgets, this hybrid design achieved a much better compression ratio than either single choice would have provided. I'll talk next about a new functional unit that we added to each processor core to accelerate elliptic curve cryptography and the modulo arithmetic operations that are behind it. This form of cryptography is the backbone behind distributed ledger technology such as blockchain. ECC is also increasingly replacing RSA-based algorithms that are used for securing communications, and that's due to its ability to achieve the same level of security with much smaller keys, ciphertext, and signature sizes. Internally, we call this the MA unit, and that stands for modulo arithmetic. So the MA unit has its own microarchitectural instruction set, and it's not visible at the software level. Instead, a single new processor instruction was added, and the ECC sign and verify operations it encompasses are implemented as a combination of firmware and hardware. So this is a new kind of accelerator that we haven't implemented before in the way that it attaches to the main pipeline and how it's driven by our firmware. I'll describe some of what makes this particular design novel and why it'll act as a blueprint for accelerators that we'll continue to build going forward. So the new unit is essentially a coprocessor, and it's attached to the back end of the pipeline. The unit is loaded, controlled, and driven by firmware post-completion, and that means that all of the execution is in order and it's non-speculative. That means that there's no branch wrong flushes, no register renaming complications, or other typical pipeline pain points to deal with. So the data loading and all the cache missing happens in the main pipeline, and the results are just passed to the core accelerator. The main critical pipeline is virtually unaffected by this type of an addition, and physically you could locate accelerators like this far away and out of the critical real estate of a typical core. This paradigm works here because the computations involved in these operations has no input or effect on the data retrieval and address generation process. Also, the accelerator is able to perform dozens to hundreds of modulo math steps using just a few double words of input data. This lightweight style of a detached, in-order accelerator works well anytime these characteristics are present. This chart shows the internal micro-instruction set that the MA unit supports. Remember that these operations are only accessible to the firmware running on the core that we call millicode. So the speedup chart at the bottom here shows how much faster public key sign and verify operations run with MA acceleration. Note that the compare point isn't against doing the same operations in pure software. It's actually against running on a Z14 using a PCI-attached Crypto Express accelerator.
The IBM mainframe plays an ever more important role in hybrid cloud environments, and as such, we've invested significantly in an environment where we can run security-sensitive applications and containers on the mainframe. So one of the challenges that exist in the industry is that hypervisor and administrator layers of any hybrid cloud environment really have access to all of the data and the applications that run underneath them. So we've introduced a new feature into the Z15 processor called Secure Execution. And the purpose of this environment is to create a vertical isolation of the application layer so that even a hypervisor or administrator can't get to the data of applications and container guests that run underneath them. While we provide this vertical isolation, we've also enhanced the horizontal isolation between different containers or guests. So, in a cloud hosting environment, you have different constituents all sharing virtualized parts of a machine, and they'll be separated from each other in a more reliable way. This is because security exposures or malicious system admins can't be exploited to bridge between neighboring containers. So this feature has been implemented through a specialized mode in the CPU, memory, and the I/O subsystem. We've introduced a new trusted firmware layer that we call the ultravisor, and that sits between the hardware and the hypervisor. We track ownership of parts of memory and safeguard access to those areas by the various components of the system through this trusted hardware and firmware layer. So a secure guest could only execute instructions from memory marked secure and owned by that specific guest. And unique IDs distinguish and isolate secure memory images from each other. So for example, if the CPU is in hypervisor mode, it won't have access to the memory pages that are tagged and owned by secure containers. And we only allow the hypervisor to actually access those pages for purposes of things like swapping memory out once the pages have been fully encrypted by the ultravisor. So what that means is the actual clear text data of the container will never be visible to the hypervisor or sysadmin. Another safeguard involves the ultravisor saving off an integrity hash and an import-export count of any memory that needs to be swapped out. This prevents a secure guest from using a block of storage that has been tampered with while it was paged out. So even though the swapped out pages are encrypted, this further step stops a malicious hypervisor from corrupting a page or even trying to replace it with an older copy of the same page. So we have hardware and firmware that have very stringent validation both in our lab and in the chain of getting them to the client and booting the system. This is a more controlled code environment than, say, a KVM hypervisor that naturally has a much larger code base and a correspondingly broader attack surface against possible bugs. So what we've done here is encapsulated some of the most central security features into a trusted and certified firmware layer that we test with every change and provide to our clients in a certified way. We're essentially shielding the actual containers from possible code bugs and from administrator attacks. So it's important to note, you can be root in your KVM, but no one can be root in our trusted firmware layer, and that alone takes away a broad set of attack vectors. One very important feature is that we've tailored the entire system to be applicable to arbitrary containers. So we don't have any restrictions on the containers in terms of the amount of memory they use, or the amount of I/O they perform, or any of these other central features. This was done because we believe that for this to be widely applicable, we can't require clients or ISVs to implement a lot of software changes to benefit from this. This feature has been implemented in the hardware, the ultravisor layer, and with just some adjustments to the hypervisor. But the containers running underneath the hypervisor, including their application code, could run as is without any changes required for exploitation. I'll wrap up here with a quick review of some of the key points. So the Z15 chipset contains an SC and a CP chip, both built in 14 nanometer SOI technology. The processors run at 5.2 gigahertz, and both chips use 17 layers of metal and around 14 miles of total wire per chip. In a fully configured water-cooled enterprise server, you have 5 fully connected draws and 240 physical cores. 190 of those cores are available to the customer, and the rest are configured as I/O assist processors, system assist processors, or spare processors. We continue to invest both in microarchitectural improvements as well as important features and functions. The Z15 generation provides a 14% single thread speedup and 25% capacity growth over our prior generation. Thank you.
Thank you, Anthony. Thank you. So let's take some questions now. First question is, what is the depth of pipeline to support this impressive 5.2 gigahertz?
So you can hear me okay, Pradeep, right?
Yes, yes.
So it's a very deep pipeline. We actually on the charts there, I have the diagram that shows it, and I'd have to count it myself because it's long, and I forget the number off the top of my head. But the pipeline is long, so you could see all the way from fetching to the decode point. We have the long in-order pipeline at the front end and quite a long one at the back end, and it extends beyond completion with the recovery unit that we talked about. So I'll get you guys the exact depth and put it in the Slack channel.
So deep pipeline, okay.
Very deep pipeline, yes.
Okay. You don't want to take a guess on number of stages. We will have to count. Okay.
Yeah, I mean, it's around 30.
Okay, and next question, what are L1 and L2 load to use latencies?
So the L1 use case, there's a 4-cycle loop for L1. So if you're loading from the cache and you feed that back into address generation and then do another load, it's about 8 cycles on top of that for an L1 miss, L2 hit.
Okay, for secure execution context, what's the isolation from firmware?
I couldn't hear the question. Could you ask that again?
For secure execution context, what is the isolation from firmware?
So the firmware mentioned in the talk is what we call the ultravisor, and that's validated, trusted firmware running on the processor core, and that actually implements the layer that sits between software above and the secure guest on the hardware. So that's an integral part of a secure guest, right? It's the custom hardware and that layer of firmware that run in conjunction to provide the security.
Okay. Your talk mentions asynchronous branch prediction. I find that exciting. That often runs ahead of iFetch. What happens if it's behind? Are the predictions dropped?
Yeah, so that's a good question. So it's a lossless algorithm, so there's no drop predictions. So often the async branch predictor is running well ahead of iFetching. But the way that works is iFetching is in order, and without branch prediction steering it, it would just react to pipeline restarts, flushes, interrupts, and such. If after, say, some type of a pipeline restart condition, the first instruction or two ends up being a predicted branch, iFetching may have gone beyond that point and just fetch sequentially. So when the prediction comes in, the instruction parsing and decoding and iFetching will react to it and throw away anything that was sequential in nature, and then it'll start delivering iText at that predicted branch. There's syncs along the front end of the pipeline, but there's a hard sync at the dispatch point if you look back at that pipeline diagram. So nothing gets dispatched until that point is known to be in sync with branch prediction. So no predictions are dropped on the floor.
Okay. Will you be willing to compare your core IPC compared to Power10, the other talk?
Well, Brian and Bill will have to talk about that and come to an agreement.
Okay. Second question, another question. For secure execution, what type of encryption algorithms are used for pages relinquished from a secure guest and for associated integrity hash?
Yeah. So the pages are encrypted. The ultravisor encrypts them before a secure guest relinquishes them for paging and things like that. So it's a XTS AES 256 encryption algorithm for encrypting the pages, and then the integrity hash is SHA-512 based.
Okay. Okay. There's another question again coming back onto 5.2 gigahertz, right? Is again as to what did you is any how did you hit that high frequency? Is this primarily deep pipelining?
So I mean, so deep pipelining is necessary for sure when you do that, but really careful design and aggressive design as well. So I mean, we play all kinds of tricks to make sure these chips run as fast as possible, down to the gate level, to power cooling and all of that. So it's, as everyone knows, designing these high frequency chips, right? There's a lot of work and there's a lot of magic that goes behind it. But yeah, that's the deep pipelining is just sort of table stakes, but there's quite a lot that has to be done to allow those high frequencies as well, all the way from power distribution to how the circuits are laid out, et cetera.
Okay. So the last question. This is a big performance efficiency improvement, power efficiency improvement. Is that a new focus, intentional new focus this time?
Yeah. So the Z15 mainframe does, in general configurations, it does consume a good amount less than Z14 that's similarly configured, but that's done primarily because of improvements in air conditioning, water cooling, power distribution with the new power supplies. From a chip perspective, the focus that we provided for making it more power efficient wasn't to try to, we don't power cell phones and laptops and things with these chips, right? These are just running in these large servers. And the focus is really on getting the highest amount that we can for performance and throughput. So the power efficient design at the processor level, that was done so that we can put 2 more cores and double the size of the caches. So we save power at the chip level so we could burn it in other areas to get more performance. So yeah, there was a lot of focus here because the chip size is the same. The power budgets for the chip are very similar to the prior generation, but we stuffed a lot more hardware into it. So that was where the focus was on power efficiency under the hood at the chip level.
Thank you, Anthony. That should sum it up. And we did finish on time. Thank you all.
Thanks, everybody.
Thank you. And keep looking at Slack and keep answering and asking questions there. Thank you. So this wraps up the session 1. And